Hello everyone and welcome to the COS 122 lecture. Here we start with chapter 1 on computer system hardware. So before or after watching this video, you should also read the corresponding chapter in the operating system's textbook. The role of an operating system is to manage the hardware and software components of a computer, and in this lecture we focus on the hardware side. The typical hardware components of a computer are the processor that executes the instructions of applications. Then we have registers, that is where the instructions to be executed next needs to be stored. And we have different components of memory in a computer. There's main memory, that is used to store data and applications that are actively used by the system. And there's disk memory that can be used to store data and applications for later usage. Input and output devices, such as a printer, a mouse, a keyboard, or a screen, are also hardware components of a computer system. So, if the user of a computer wants to run a software application, then the operating system is in charge of managing the hardware components that are required in order to execute the application. And this also involves the scheduling of applications, which ensures that the entire system is running efficiently. Here we have an overview of the basic hardware components of a computer system, which are one or multiple processors, the main memory of the computer, input and output modules, and a system bus. In the following, we will have a look at each of these components and their particular role in a computer system. We start with the processor. If there's only one processor in a computer, then this is also known as a central processing unit, CPU, but there might be also multiple processors in a single computer system. The processor controls the operation of the computer. An application consists of a number of instructions, and in order to run an application, the processor loads the instructions into its registers and then executes them. And those instructions are typically arithmetic or logical operations on data. A bit later, we will see some examples of instructions that get executed by a CPU. But before that, we have to first introduce the other hardware components in a system. Another major hardware component of a computer is the main memory. The purpose of memory is to store data and applications. And as we already said, applications consist of sequences of instructions. In contrast to disk memory, the main memory is volatile. That means the content of the main memory gets lost if the computer is switched off. In contrast, if we have data stored on a hard disk memory, then this data will be still there after we have restarted the computer system. Main memory is also known by the alternative names real memory or primary memory, whereas hard drive memory is known as secondary memory. The data that is stored in the memory may result from a user input. For instance, if the user makes use of a keyboard in order to input a sentence, this will be eventually stored as data in the memory of the computer system. And for many computational tasks, it may be also necessary to output data that is stored in the memory. For instance, a screen or a printer may be used to output the data. Keyboard, printer, and screen belong to the external environment of a computer system. And in order to move data between the computer and its external environment, so-called input and output modules are used, which also belong to the major hardware components of a computer system. And finally, we have the system bus as a hardware component, which is a communication line among the processor, the main memory, and the input and output modules. So the system bus ensures that the processor has access to the memory and also that data stored in the memory can be transferred to the input and output modules. And here we have an illustration that shows how the basic hardware components are interconnected in a computer system. We have the processor, which is called CPU here. Then we have the main memory, and the input-output modules. And all of these components are connected via the system bus, which allows them to communicate. Let us have a detailed look at the main memory first. It consists of a set of locations that are numbered from 0 to n-1, and the numbers are the addresses that define the locations. The locations can store applications or data, and we know that an application consists of a number of instructions. In the red box, we see a list of instructions that may correspond to a program or an application. Now we will have a look at the CPU. Via the system bus, it has access to the main memory, so it can load and store instructions or data. The CPU consists of a number of registers and an execution unit. Registers are small memory units that can store a single instruction or a piece of data. The program counter register PC is used to store the address of the next instruction to be executed. Then we have the instruction register IR. That is where the instruction to be executed next will be stored. An instruction is typically an operation on data. If data needs to be manipulated, then the memory address register MAR will store the address where the data can be found in the memory. So the piece of data that is stored at the address in the MAR will be loaded in the memory buffer register MBR. For instance, if the memory address register contains the address X, then the data at that address will be loaded into the memory buffer register, which is the data Y here in this example. The CPU also has an input-output address register and an input-output buffer register, which are used in order to access data from the input and output modules. Now we have a detailed look at the input-output module. In a computer system, there will be one input-output module for each external device. So one for a keyboard, one for a mouse, and so on. An input-output module has an internal memory buffer, which is also characterized by a set of locations that are defined by addresses. For instance, a keyboard input will be first stored as data in the buffer of the corresponding input and output module. And then the CPU can access the data via the system bus. A bit later, we will have a more detailed look on how instructions and data get loaded into registers, how instructions are executed, and how data gets updated. Before that, we will have a brief look at the evolution of hardware in the past decades. One big step in the evolution of hardware was the invention of the microprocessor. While older CPUs were generally distributed over multiple chips, the microprocessor was the first CPU that came on a single chip. Computers used to be huge machines, but with the introduction of the microprocessor, it became possible to introduce small desktop computers, laptops, and handheld devices such as tablets. Today, microprocessors have become the fastest general-purpose processors that are available on the market. And we even have microprocessors that are multiprocessors, which means multiple processor cores are integrated on a single chip. For instance, in your own computer or laptop, you may have an Intel i7 processor. That one comes with 8 cores and is therefore capable of executing multiple applications in parallel. Another milestone in the history of hardware was the introduction of graphical processing units. Standard CPUs are general-purpose processors that can perform many different kinds of operations. In contrast, a GPU is a special-purpose processor that is restricted to graphical computations. For such graphical computations, GPUs are much more efficient than standard CPUs. And today, graphical processing units are even used for numerical data processing tasks. Because the operations that are used in data processing are very similar to those that are used in graphical image processing. Then we have digital signal processors, DSPs. They are used for streaming audio or video signals. Besides that, there also exist special purpose DSPs for encoding and decoding of speech and for encryption of data. And finally, we have the so-called system on a chip. On the picture here, you can see the so-called Raspberry Pi, which is an entire computer system on a single board. So you can basically plug in a screen, a keyboard, and a mouse, and then you have a fully functional computer. Since everything is integrated into a single chip, the communication between the components is fast and easy, which makes a system on a chip typically very efficient. Now, after this brief overview of the evolution of hardware, we look again at the execution of instructions by the processor. We have already seen that instructions are typically contained in the main memory, and they need to be loaded into the registers of the processor in order to get executed. So, in the simplest form, the execution of an instruction by the processor happens in two steps. In the first step, the processor reads an instruction from memory, and for the necessary communication, the system bus is used. And in the second step, the processor executes the instruction via its execution unit. The execution of an instruction typically produces some new data. The processing that is required for a single instruction is called an instruction cycle. We will later see that there exist multi-stage instruction cycles, but in the simplest case, it is a two-stage cycle. We have the two stages that we already introduced on the previous slide, which are fetch of the next instruction and the execution of the instruction. If a computer is turned on, then the instruction cycle will immediately start. The processor will first fetch and then execute an instruction, and then continue in the same manner with the next instruction and so on. And this cycle will not stop until either the computer is turned off or until some computer error occurs that halts the processor. So now, after we have identified the two stages of an instruction cycle, we now look at the details what exactly will happen when the processor fetches an instruction. Remember, one of the components of a processor is a so-called program counter register. It stores the memory address of the next instruction to be fetched and executed. In the blue box you see an example of a program counter. So here it contains the binary number 0100, which corresponds to the decimal number 4. In the instruction fetch step, the processor will load the instruction that can be found at that memory address into its instruction register. So in the main memory, at address 0100, there may be the instruction stored that is shown here in the red box. As you can see, an instruction is typically encoded in a bit string. The processor will know how to interpret the bit string. It may correspond to a mathematical operation like multiplication or addition. After the instruction at the current program counter address has been loaded, the program counter gets incremented. So in our example, the address 4 in the program counter register will be replaced by the address 5, and that means in the next instruction cycle, the instruction at location 5 will be loaded and executed. And in the following cycles, the instructions at the addresses 6, 7, and 8 and so on will be fetched and executed. So we have seen what happens in the instruction fetch step. The next instruction to be executed will be loaded into the instruction register of the processor. Now this instruction is ready for execution. The processor will interpret the binary instruction and will perform the required action. These actions typically fall in 4 different categories. We have process memory actions, where data is transferred from the processor to memory or from the memory to the processor. Then we have processor input-output actions, where data is transferred between the processor and an external device. The external device may be, for instance, a keyboard or a screen, and the transfer will make use of the input and output module of this device. And we also have data processing actions. that is where the processor performs logical or arithmetic operations on data, for instance, adding two integer numbers. And finally, we have control actions. That is when the program counter shall not be just incremented, but set to a specific address. For instance, if there is some loop in a program that is stored in the main memory, then that requires at some point the program counter to be set back to some earlier value. For instance, if the program counter is currently 5, then a control action may set it back to 0 if 0 indicates the start of a loop of a program that is stored in the memory. So now we will look at an example on how the processor will interpret a binary encoded instruction. In general, there exist different instruction formats, and we assume that our example processor can handle 16-bit instructions. Moreover, we assume that the first 4 bits of an instruction contain the so-called opcode that characterizes the type of operation. And the latter 12 bits characterize the address in memory where the data can be found to which the operation shall be applied. In the green box, you can see some example opcodes that we assume for our processor. So the opcode binary 1 corresponds to a load operation. Binary 2 corresponds to a store operation, and binary 5 corresponds to an addition operation. In the red box, we have an example of one full instruction. We can see that the opcode, the first 4 bits, equals to binary 1, so it corresponds to a load operation. The remaining 12 bits represent the memory address from where data shall be loaded. The data will be loaded from memory into the accumulator, which is one of the processor's internal registers. If we translate the binary instruction into a hexadecimal instruction, we get the number 1940. So this tells us that the memory content at address 940 shall be loaded into the accumulator register. The memory content may be either another instruction, where we again have 4 bits of an opcode and 12 bits of an address, or the memory content may be a piece of data, for instance an integer number. Then the first bit would be the sign of the number, and the remaining 15 bits would be the magnitude. So now, after we have seen how the instruction fetch and the instruction execution works, we will now have a look at the execution of a small program that is stored in the main memory of a computer. In the black box on the left, you can see the current configuration of our system. We have the main memory that contains a small program at the addresses 300, 301, and 302. The program consists of the 3 instructions that are stored here. Moreover, we also have some data stored in the main memory, and the data can be found at the addresses 940 and 941. Then we can see our CPU registers depicted in gray. The program counter contains the number 300, which is the memory address from which the next instruction shall be fetched. We can see that at memory address 300, we have the instruction 1940, and this instruction gets loaded into the instruction register of the CPU. The opcode of this instruction is the number 1, and if you look at the green box at the bottom, then you can see that an opcode 1 corresponds to a load operation. We have that the memory content at address 940 shall be loaded into the accumulator register of the CPU. And this will happen in the next execution stage, which is depicted in the black box on the right. As you can see, now the accumulator register, which was previously empty, now contains a piece of data that is stored at memory address 940. And part of each execution of an instruction is that the program counter gets incremented. So now it has been set from 300 to 301. So we have completed the first instruction cycle of our simple program, and now we continue with the second cycle. The second cycle is highlighted in red. We can see that in the fetch stage, the current program counter holds the number 301. So the instruction at memory address 301 will be loaded into the instruction register. The opcode of the loaded instruction is the number 5. And if we look at our list of opcodes, then we can see that the number 5 corresponds to an addition operation. We are done with the fetch stage, and we now continue with the execution stage of the second cycle. The address part of our addition instruction to be executed is 941. So the data that is stored at memory address 941 shall be added to the content of the accumulator, and the result should be also stored in the accumulator. The memory content at 941 is the number 2, and the content of the accumulator is the number 3. So if we add 3 and 2, we get the number 5, and 5 will be stored in the accumulator register. And again, a part of each execution stage is that the program counter gets incremented. Here the program counter gets set to the number 302, which is the address of the instruction that shall be loaded and executed next. In the next instruction cycle, which is again highlighted in red, we start with the fetch stage. The program counter is currently 302, so the instruction at memory address 302 is loaded into the instruction register. And this instruction corresponds to the number 2941. So the opcode here is the number 2, and if we look at our opcode list, then we see that the number 2 corresponds to a store operation. In particular, the content of the accumulator register shall be stored in memory at the address that is followed by the opcode. So this is the address 941 in our example. Now we continue with the final execution stage. As you can see, there are now some blank fields in the memory and also in the CPU. So as a small exercise for yourself, you can pause the video here and figure out what will be the content of memory and of the registers after the final execution step. We will then discuss the solution on the next slide. So here's the solution. In the instruction register, we have the store operation 2, which is the opcode, 941, which is the address where the content of the accumulator shall be stored. We can see that the accumulator content, which is the number 5, has been stored at the memory address 941, which also now contains the number 5. And again, the program counter has been incremented. It now contains the number 303, which is the address of the next instruction to be executed. We will stop here with our example after the 3 instruction cycles that we illustrated. But you can easily imagine how the processor will continue executing instructions, which will only stop if the system gets turned off. We will now look at a concept that plays an important role when it comes to the execution of programs by the processor, and this is the interrupt concept. In the previous examples, we always assumed that if the processor executes a user program, the program will always run from the beginning until it terminates, and then maybe some second user program will be executed. However, in a computer system, this is not always the case. A running user program may get interrupted by another program and then resumed at a later stage. An interrupt is a mechanism by which input and output modules can interrupt the normal program execution of the processor. We will look at a number of examples that will show you that interrupts can increase the efficiency of a computer system. The general idea behind interrupts is as follows. External devices, such as a printer, are much slower than the processor. Now, without an interrupt concept, a user program that makes use of a printer may have to wait until a printing job is completely done, until the program can continue running. But if there exists an interrupt concept, then the processor and the external device, such as a printer, can run in parallel. The printing job is running, and at the same time the execution of the user program continues. Only once the printing job is done, the input-output module of the printer will send an interrupt signal to the processor. The user program will be only interrupted for a short time in order to let the processor finalize the input-output program corresponding to the printing job. The printer here is only one possible example of an external device that may cause an interrupt. But interrupts can be also caused by other external devices, such as a keyboard or a screen. So interrupts of a running program are mainly caused by input and output modules corresponding to external devices. Besides input and output interrupts, there also exist further classes of interrupts. There exist program interrupts that are related to exception handling in software programs, for instance the handling of arithmetic overflow or division by zero. Timer interrupts are generated by a system clock, and they allow the operating system to perform certain functions on a regular basis, for instance an automatic backup or a checking for updates. And finally we have hardware interrupts that are generated by a failure of a hardware component or a failure of power. In this course, we will mainly look at input and output interrupts. And we will now discuss an extensive example based on a printer. In the first part, we consider the case where there's no interrupt concept. We have a user program that is executed on the CPU. After the program segment that is marked with the number 1 in the illustration, the user program makes a write call. The write call will pause the user program. The processor will no longer execute the user program, but will start executing an input-output program that is in charge of the printer. The red arrows in the illustration indicate what the processor is currently doing. So after executing segment 1 of the user program, the processor will start executing segment 4 of the input and output program. We assume that in program segment 4, the data is prepared for being printed. So the input-output program copies data into the write buffer of the printer. Once that is done, the input-output program issues some input-output command. So the data is in the buffer and the printer starts printing. The dashed line indicates the time when the printer is printing. At the same time, the CPU is not doing anything, it just waits until the printing job is completed. Once the printing is completed, the processor will execute segment 5 of the input and output program. We can assume that this part of the input-output program will notify the system about the success or failure of the printing job. Now the input and output program terminates, and the processor resumes the user program. After a long time of waiting, we now have that finally segment 2 of the user program will be executed. In particular, we had a big time frame where the processor was not doing anything and just waiting for the printing job to be done. In the second part of the example, we will see how the concept of interrupts will allow us to reduce the time where the processor is not doing anything, which will give us more efficiency in the system. So in the case of interrupts, our scenario still looks the same. We have a user program that issues a print command at some point, which will start an input and output program that is in charge of a printer. after program segment 4, the input and output program will issue an input and output command and let the printer start printing. Now the input-output program is blocked. It has to wait until the printing job is done, until it can run to completion. However, now instead of letting the entire system wait, the processor will resume the user program. So while the printer is printing, the processor will execute segment 2A of the user program. At one point, the printing job will be done. And then the input and output module that is in charge of the printer will send a so-called interrupt signal to the processor. The point in time when the interrupt signal arrives is marked with a black cross here. The processor will now interrupt the execution of the user program and start executing segment 5 of the input and output program. There's a routine that is in charge of resuming the input and output program, and that is called the interrupt handler. Once the interrupt handler has ensured that the input and output program has run to completion, the processor will resume the user program. That means in our example, now segment 2B of the user program will be executed on the CPU. Such an interrupt that gets caused by an external device, like the printer in our example, can occur at any time. On the upcoming slides, we will also discuss what steps need to be taken in order to safely resume the user program after an interrupt has occurred. It involves to save the state of the user program, such that it can be later restored after the interrupt has been handled. What we can already see is that in contrast to the first example, where we had no interrupts, here we have that the processor is never idling. So the interrupt concept can give us a better utilization of the processor and therefore also more efficiency in the computer system. The interrupt concept also leads to an extended instruction cycle where we now have 3 stages. Again, each cycle starts with the fetch of the next instruction from the memory, followed by the second stage where the instruction gets executed. Now, if interrupts are enabled, then we have a third stage where the processor checks whether an interrupt signal has been received. If that is the case, then the processor will suspend the execution of the current user program and it will execute an interrupt handler routine. The interrupt handling routine will save the state of the user program and it will determine which input and output module has caused the interrupt. Then it will take the corresponding actions, typically the execution of an input and output program, and afterwards it will resume the user program. If you look at this diagram here, then it is important to note that the processor will only check for an interrupt after an execution stage has been completed. So the processor will never check for an instruction after the fetched stage. And the processor will also never stop an instruction execution that is currently in progress. It will always wait until the current instruction is executed to completion until it checks if another interrupt has been received. So obviously, if we have a system where interrupts are enabled, that involves some extra computational steps. The state of an interrupted program needs to be saved in memory, which will take some time. And the interrupt handler is an extra program that needs to be executed each time an interrupt signal arrives. However, we will typically still get a gain of efficiency if we use interrupts. If we look at our printer examples again, where we had one case with no interrupts and a second case with interrupts, then we can draw the following corresponding timing diagrams. The green parts of the diagrams correspond to the execution of the user program. The gray parts correspond to the input and output program, and the black part corresponds to the time where the processor is not doing anything but just idling. So with no interrupts, we have a time frame where the processor is completely inactive. It just waits until the printer is done with printing. On the other side, if interrupts are enabled, then a part of the user program can be still executed while the printer is running. We now have a time frame where the execution of the user program and the printing happens in parallel. In the end, we get a better performance if interrupts are enabled. We can see that the user program and the input and output program will terminate earlier than in the case where we have no interrupts. Now, after we have illustrated the performance advantages of interrupts, we will now have a detailed look on what has to happen in order to safely interrupt and then later resume a user program. In the blue box, you can see the content of memory and the registers at the point in time when an interrupt signal is received by the processor. You can see the user program is stored somewhere at the bottom of the memory. Then, in the middle of the memory, starting at address Y, the interrupt service routine is stored. And at the top of the memory, we have a control stack that is currently empty. Now, if you look at the register content, then we can see that the program counter is currently n+1. That means that the user program instruction at address n has already been executed, and the next instruction to be executed is at address n+1. We can also see that one of the registers is the stack pointer, which points at the top of the control stack. The current top of the stack is the address T, which means that the stack is still empty. Now the incoming interrupt will be handled as follows. The content of all the registers will be stored on the stack. That is, the content of the general registers will be pushed onto the stack, then the program counter will be pushed on the stack, and the stack pointer will be updated. Now we have saved the state of the user program on the stack. What needs to happen next is that the interrupt service routine must be prepared for being executed in the next step. For this, the program counter gets updated to the address Y, which is the starting point of the interrupt service routine in the main memory. So in the next instruction cycles, the processor will execute the instructions that are stored at the addresses Y to Y+L. This corresponds to the full execution of the interrupt service routine, and afterwards we want to resume the user program. For this, we look at the green box, and this indicates how the state of the user program gets loaded from the stack back into the registers. After the interrupt service routine has run to completion, the program counter is Y+L+1. If we load the status of the user program from the stack, then the program counter gets updated to n+1. This is the address of the next instruction of the user program to be executed. Moreover, we also restore the contents of the general registers by taking them from the stack. The stack is now empty again, so correspondingly the stack pointer gets updated again to the address T. Now we have completely restored the original state of the user program, and the processor can now safely continue with the execution of the user program. So far, we have only discussed the case of a single interrupt. However, additional interrupts can occur while one interrupt is currently handled. For instance, a user program may get interrupted by a printer. Now, while the printer interrupt service routine handles the printing request, another interrupt signal caused by a keyboard may be received. In operating systems, there are generally two different approaches to deal with multiple interrupts at the same time. Interrupts can be handled in a strictly sequential manner, which means the first interrupt that comes in will be handled first, and all later incoming interrupts have to wait until the first interrupt has been handled. The second approach is to use a priority scheme. For instance, the operating system may assign a higher priority to a keyboard than to a printer. That means if a printing interrupt is handled and another keyboard interrupt comes in, then this will interrupt the printing handler. However, a printing handler would never interrupt a keyboard handler because the keyboard handler has a higher priority. On the upcoming slides, we discuss more detailed examples on how the two approaches handle multiple interrupts. We start with an example on sequential interrupt handling. On the right, we see an illustration of a user program, and we assume that the execution of the user program by the processor starts at time step 0. Now at time step 10, the processor receives an interrupt signal from some external device X. The execution of the user program will be stopped, and the processor will start executing the interrupt handler X. Now, while the interrupt handler X is running, an external device Y sends another interrupt signal to the processor. Since we assume sequential interrupt handling, Y has to wait until the interrupt handler X has terminated. That happens at time step 20. Interrupt handler X finishes and interrupt handler Y starts running. And once interrupt handler Y terminates, the processor resumes the user program, which happens at time step 30. Now we look at an example for interrupt handling where we assume a priority scheme. The external devices that may cause an interrupt here are a printer, a hard disk, and a keyboard. And we assume that the operating system makes use of a priority order where the printer has the lowest priority, followed by the hard disk with medium priority, followed by the keyboard with the highest priority. Our example starts again with the execution of the user program at time step 0. At time step 10, the processor receives an interrupt signal from the printer. Consequently, the execution of the user program will be stopped, and the processor will start executing the printer interrupt service routine. We can see that at time step 15, another interrupt signal, now caused by the keyboard communication device, is received. Since the keyboard has a higher priority than the printer, the execution of the printer interrupt service routine will be stopped. The processor will now start to execute the communication interrupt service routine corresponding to the keyboard. Now, while the communication interrupt service routine is running, a third interrupt signal comes in. This interrupt signal is caused by the hard disk. The hard disk has a lower priority than the keyboard communication device. Therefore, the disk interrupt service routine has to wait until the communication interrupt service routine has terminated. And this happens at time step 25. Now we have two active interrupt service routines, one for the disk and one for the printer. Since the disk has a higher priority than the printer, the disk interrupt service routine will be executed next. It terminates at time step 35, and only then the printer interrupt service routine will be resumed. It runs to completion, which happens at time step 40, and now that all interrupts have been handled, the processor will continue with the user program. Interrupt handling with priorities has the advantage that it allows to incorporate time-critical needs. For instance, handling a keyboard input may be more time-critical than handling a printer output. And this is because a keyboard module can only buffer a limited number of input characters until it comes to a buffer overflow. So by giving the keyboard a higher priority than other devices, it will be serviced more often. And that makes it less likely that the buffer of the keyboard module overflows. We finished the first lecture on chapter 1 here, and in the next lecture we continue with the topic computer memory.